let us continue from where we were. So in yesterday's lecture, we'd used an unnecessarily cumbersome method, but anyway, we'll finish it since we started it, to compute the following. We computed QBRST on alpha mu minus 1 on down k was equal to k mu times c minus 1 down k. Right? We computed QBRST on c minus 1 on down k was equal to 0. And what we were left to compute was QB on b minus 1 on down k. Okay. Now, in order to do this calculation by the unnecessarily silly method I employed last class, what do we have to do? We need to find the operator dual to this state. But we did that last class. Do you remember the operator dual to this state was c times e to the pi kx? And then we found that when we acted on it with b minus 1, that just removed the c. Right? Do you remember that? Because the b minus 1 was integral bz, and then the op just removed the c. Okay, so this thing, in order to compute that, we need the BRST operator acting on just e to the pi k dot x. Right? So that's particularly easy because this is c times t times e to the pi k dot x. And what we want to do is find the pole in this. Okay. Now, there is, of course, okay, so let's just do that. So this is minus 1 by alpha prime c del x mu on e to the pi k dot x. Okay, now we get two terms. We get the term when we just take all of t and contract with this guy. Okay, so when we take, oh, I'm sorry. Yeah, but no, that's okay. Yeah, so when we take, I've written c times t because anything that was just the ghosts vanishes because we're just doing it on e to the pi k dot x. Right, so we take all of this t and act on this guy. So that will give us c of z times c of z times alpha prime k squared by 4 times e to the pi k dot x by z squared. But what was alpha prime k squared by 4? It was the mass, and at this level, what was it? 0. Remember, because we wanted all of L0 equal to 0. L0 got contributions from the ghost part, which was minus 1 in the vacuum. But then we increased it by 1 by this b minus 1 oscillator. So the ghost part was 0. So the matter part had to be 0. Okay? So this term, though it's there, in this particular case is 0. So the only term will actually occur when one of these contract with one of these. Okay, that will give a single pole rather than double pole. And can you say that up to constants which are not important, we'll get c del x mu times k mu e to the pi k dot x. It's the usual story. You contract one of these with this. It'll get back the exponent with a factor of k mu. There would be various factors of 2 because there would be two ways of contracting in alpha prime and so on, but we don't care about all that. Is this clear? Okay. Now, c del x mu times e to the pi k dot x was precisely alpha mu minus 1 acting on down k. Right? Because down k was C times e to the pi k dot x, and alpha minus 1 was del x mu. Is it clear? That was the starting point of the calculation. We started with this quantity being C times del x mu times e to the pi k dot x. Okay, so this is k mu times alpha minus 1 mu on down k. So now we can fill in the last part. This up to some constants which are not important. This is, so I should write proportional to, all of these are proportional to. No, this one is equal to. Alpha is proportional to, okay, that's proportional to k mu alpha minus 1 mu down k. Okay? Now that we've got all these results, computing the cohomology at this level is totally trivial. Okay? How do we compute the cohomology at this order? Well, first we want the states that are killed by Q. And then we want the states that are not also Q exact. So which states are killed by Q? Let's see, what about states of this form? The states that are killed by Q are of the states of the form E mu alpha minus 1 mu on down k, such that E dot k is equal to 0.
Because this is massless, is this the same as saying that E is equal to some constant times k?
No, it's not. You see, that's one way it could happen.
Right.
See, the photon's moving like this. Yeah. Being in the k direction is one way to do it. The other way is just to be perpendicular. Okay? These will be the trivial ones. These will be the pure gauge ones. So the perpendicular ones that are the real photons, or the real gravitons. Okay? But you're right, that one way of ensuring this is E being proportional to k. But of course there are others. Okay, so the condition that Q annihilates it in the matter sector is a condition on the polarization. E dot k is equal to 0. Also, the states with C minus 1, so these states are okay. And then C minus 1 on down k is okay from the point of view, these are the Q closed. Clearly, B minus 1 is not Q closed. Right? Because it always gives you something. So you act with Q on B minus 1 and down k, you never get 0. Okay? You act with Q on one of these states such that this condition is not met, you don't get 0. But if this condition is met, or if you act on a C minus 1 on down k, you get 0. Okay, so we've gone from 28 to 26. Because we've killed two oscillators. Which ones have we killed?
One of the above and the second one.
Exactly. What we've killed is the B oscillator, B minus 1 state, and the one state that is not orthogonal to k. I mean, we've killed the states that are not orthogonal to k, but that's one condition. On the possible 26 polarizations, there's one condition of orthogonality. So we're left with a 25-dimensional polarization space. Okay? So we've been left with 26 oscillators. However, physical states are not just associated with things that are killed by Q. Anything that is Q exact is to be treated as equivalent. Addition of something that's Q exact is to be treated as something equivalent to the original state, to be treated as 0. So we've already seen from here that anything with a C minus 1 is Q exact. Okay? So C minus 1 states are Q exact. And also, we've seen from here that anything with epsilon proportional to K is Q exact because it's Q1 and B minus 1. Okay? That kills another 2 states. So we've gone from 28 to 24. In particular, we have seen that our states at this cohomology level can always be chosen to have no ghost component. They must have no B minus 1. But they can always be chosen also not to have a C minus 1. Right? Whether you put a C minus 1 or not is of course up to you. It's a cohomology class. You can always choose the cohomology class not to have the C minus 1. Okay? Moreover, states must have epsilon dot k is equal to 0. And among those states, as you pointed out, there's one way of satisfying this condition to be chosen such that epsilon is proportional to k. Epsilons that differ by proportionality to k are not different states. Okay? Now this is of course a very familiar condition. This is the condition of gauge transformations. We know that at the massless level at one sect or one half we get photons, or with both of them we get gravitons. Okay? Since the gauge invariance is splitting to left and right, I'll say photons, though I often mean it in the context of gravitons. Okay? What we're saying is that if you take A mu and you make it proportional to K mu, that is pure gauge. Which is the statement that a gauge field that is a derivative of scalar is pure gauge. Okay? And a pure gauge photon scattering with anything should give you 0. Or if you take a photon and add a pure gauge element to it and you do the scattering, you shouldn't get anything different. Okay? So this Q equivalence, the equivalence that says epsilon proportional to K is Q exact, is a sophisticated string theory version
Of what identity?
of basically saying that gauge equivalent states that differ just by a gauge transformation in QED, in electromagnetic dynamics, are the same. Okay? In fact, this is precisely what we would get if we did BRST quantization of electrodynamics. If we did BRST quantization of electrodynamics, we would have our own BRST symmetry. We work in Lorentz gauge, and we will find from that point of view that A's that differ by gauge transformations are BRST exact. Okay? So this BRST of string theory has in it, inbuilt in it, the BRST symmetry of electrodynamics. Okay? And in particular this, in the -1 sector, all we are really exploring in this sector where we are just looking at -1 here, or the physical degrees of freedom are that of the photon. And this is precisely the field content we would get by looking at the BRST quantization of a photon just by Weinberg's techniques in 26 dimensions. So this is just the first quantized version of that BRST, the BRST treatment of electrodynamics in Weinberg. Okay, if we were to do that. Okay, so there's nothing mysterious about this. There's nothing mysterious about this, and it's very nice. Okay, so you see that this at this level, the level of massless states, the BRST quantization, firstly, A recovers the Hilbert space we got very early in the lecture from light cone very early in the course from light cone quantization, because we got only 24 states. Okay, and moreover, it does it in a way that is very reminiscent of field theory BRST construction.
This is space-time gauge symmetry that you are seeing.
Yes.
Is there any way of seeing that from axiom? It's a own cell.
Well, okay, but you would have one of these for every k. So of course this is linearized. This is like a linearized, that linearized kind of BRST of that structure. But since you have one of these at every k, it's like a field theory.
In the level of Lagrangian,
Yes.
that was written in terms of space-time coordinates x mu.
Which was written? The field theory. Field theory was written. Yes.
There are indices like mu, which are space-time coordinates.
Correct.
And these are the gauge fields in that coordinate system.
These are the modes of the gauge field in that coordinate system.
Modes of the gauge field in this coordinate.
Now let's look at C minus down k. That will be the mode of the ghost of electromagnetism.
Modes of the ghost. But where is this symmetry coming from? The Lagrangian perspective, is there any way of seeing that this symmetry is there? It's not that, right?
I didn't understand.
I am given a Lagrangian.
The Lagrangian meaning the Lagrangian of electrodynamics.
Lagrangian of this theory, this boson close to it.
Oh, you want to do it you want the space-time Lagrangian.
Yes.
But in closed string theory, there's no gauge states, right? Such spin one states, one particle string one oscillator state.
No, but then you would have one oscillator on left and one oscillator on the right.
So if you do an effective,
So it would be the same thing. Gravity instead of
if
field
you
theory.
do an effective field theory for these modes,
Yes.
there's a light enough you can do that.
Yes.
probably.
Yes.
So if you do that, then you will get some effective Lagrangian for these modes A mu. If you write this A mu,
Exactly.
that will have this gauge invariance,
That will have this gauge invariance. We're seeing the linearized gauge invariance here.
linearized gauge invariance. So it must be there in that Lagrangian, whole nonlinear Lagrangian. It was somewhere hidden. Right?
What, this gauge invariance was hidden?
Yeah.
Yes. Okay. So you are asking the question, can you write down string theory in a way that sees the full nonlinear symmetry, nonlinear gauge symmetry? Okay. This is the question. This is a question that has been much asked starting from the mid-80s. The answer to that question is string field theory. Okay. String field theory is a formal way of writing on the whole Lagrangian of string theory. Okay. That sees nonlinearly the gauge invariance.
So this has a nonlinear extension. And
This has a nonlinear extension, exactly. I'll tell you schematically. In the open string field theory, it's very simple. I'll tell you schematically. Okay. I won't tell you what all the symbols mean, but I'll just write down some symbols and. You write down an action on some space, okay? That doesn't matter, but I won't, because it's a long story. No, this is just, but that's a different issue. This is on the space of, it doesn't matter. It doesn't matter. It's you write down some sort of action.
this go ahead. The names doesn't matter.
Yeah, and the point is that psi, this is the nonlinear part of it, and this is the linear part of it because it's quadratic. It gives you linear equations of motion, and this is the nonlinear part of the action. This is a star product of some sort. Okay. Now, if we ignore this, then the transformation psi goes to psi plus q times anything is a symmetry. If we include this, we need to change this a bit. Okay, and in fact, it goes to psi plus chi star psi. It's very much like the nonlinear part of Yang-Mills theory. Okay, so in open string field theory, this is Witten's open string field theory. This is well understood and well developed. It's much uglier in closed string field theory. But recently, Ashok and collaborators have really developed it to make it usable. So this is also understood in some sense, in an uglier way, in closed string field theory. So such a thing exists and has also recently been made useful. Okay, fine. And this explicitly now, if you take that closed string field theory, you integrate out the massive modes, explicitly you will get electromagnetism with the ghosts. Okay, and these C minus 1s would be the modes of those quotients. Okay, so it's a very precise, the whole thing is very precise. Okay, more questions or comments? Linear and nonlinear. You see, anytime you've got, I haven't told you what space all this lives in, but very schematically, anytime you've got a Lagrangian which is quadratic, this is some field, this is some other field. What it means, I'm not telling you. But you see, this psi is the same in some notation as this psi. Okay, and this psi, here this is quadratic in the fields of the theory. Here this is cubic in the fields of the theory. So if you just get this part of the action, you'd be doing the free theory, because the equations of motions would be linear. If we added this part of the action as well, we'd be doing an interacting theory, because the equations of motion would have a linear part and a quadratic part. Okay? So we ignore, if we look at very small amplitudes, this term can be ignored compared to this. The theory becomes effectively free. And if you do that, this is the action. This action has exactly the symmetry that we've been studying. That is psi going to q psi. That is psi, some state, and q times that psi plus q times that psi. Another state is the same state. Now, in the Niels question was, does this get enhanced to a nonlinear symmetry with a nonlinear BRST invariance? You know, the structure of the nonlinear gauge invariance. And it does, because the whole theory is interacting. And it does in a very concrete way. And that's what I wanted to say. So when we do this for gravity, for instance, the gauge symmetry is non-abelian. And that whole non-abelian structure, of course, arises in string theory. Okay, we don't need to obsess about this stuff. Just, yeah.
This is like formally equivalent to what we are doing. This is not, it's not like...
It's nothing new. And for a long time, you know, string field theory was studied and studied and studied from the 1980s. And for a long time, in my opinion, okay, people have very different opinions on this, but as far as I can tell, for a long time, until about 3 or 4 years ago, string field theory generated like 10, maybe 1,000 papers or 2,000 papers, but no new information that you could not get more easily from what we were doing. However, this has changed. This has changed over the last 3 or 4 years with the work of Ashok. Ashok has very carefully studied, and various other people, but principally Ashok. Ashok has very carefully studied issues concerning unitarity in string theory, infrared divergence in string theory. Recently, the last week, he had a paper on crossing symmetry in string theory. Okay? All these issues that, from what we are doing, you feel it's probably going to work out, but had never been shown. Using string field theory, he's shown A, string perturbation theory is well defined at every order. B, it's unitary at every order. C, it obeys crossing invariance to the extent that it should. You know, all these things that were sort of vaguely believed have been shown and could not easily be shown using what we're doing. So this stuff reduces to what we're doing, but it's a little better. Let me tell you why it's a little better.
You will be telling us all this.
It depends. It depends on how much time we have. I would love to, because it'll be forced me to learn it. I would love to. If we continue this course next semester, we'll...
Just one question on a comment that you just made about string perturbation theory. So I don't know whether this is correct, but I think in mid-80s, Gross and Pedival had shown that string perturbation theory is not even Bodel summable something, and so
right.
How does this work out from the same?
No, it makes no contact with that. That's a question of summing the string perturbation series. What Ashok has been doing is just looking at it term by term in perturbation. You see, what people have done previously, if you look, you look at the last chapter in this book of Pulchinski, he will claim some sort of proof that string theory is unitary, infrared, ultraviolet finite, unitary, and you look at the proof, it's not a proof. It's some argument which, with a million possible subtleties. The thing that really convinced people, of course, was that you can do some calculations. You never run into trouble, but okay, calculations you do up to 2 loops. That was basically state of art. You do 2 loops. Doing 3 loops from this point of view, actually there are some subtle ambiguities. So the first thing Ashok had to do was to give prescriptions to clean up those. I'm being unfair when I'm saying just Ashok. Witten played a role and various other people, but principally Ashok. Okay. What he had to do was to, whenever there was an ambiguity in the prescription, define it clearly. Let me tell you why. Actually, nobody has asked me this, but something that you might have, as we go on, something that would have occurred to somebody to ask is this. Look, you keep saying in string theory, what we can do is on-shell scattering amplitudes. Right? For instance, something that is clear from what we've been doing is that the only vertex operators that are BRST closed are the on-shell ones. This is this L0 equals 0 condition.
Things in the middle can run off-shell.
What?
Things in the loop.
Okay, that may be a matter of philosophy. That's some formalism issue. No, but there's a more serious issue. The serious issue is, how do we know what the right on-shell condition is? Now, string theory tells us the on-shell condition classically. But of course, we have experience in quantum field theory. You've got a particle which has a classical mass m. You do 1 loop correction to that, its mass gets corrected. Okay? So now, if I want to calculate the scattering of something, correct up to 3rd order in perturbation theory. If the philosophy is we should do only on-shell calculations, I should do the calculation.
I also find that nothing is wrong with the on-shell condition.
I should do the calculation with the corrected on-shell condition.
Yes, if you things have divergences, that can change.
That can change. That's right. However, the formalism of this theory is somehow, it's like I'm only allowed to put Q exact things, and Q is defined in the classical theory. I'm going to get Q squared. This is what it gives me. So how do I do that? How do I move away from classical on-shell to actual on-shell? How do I do it practically speaking? Now, the way we do it in quantum field theory is very clear. We just work off-shell from the beginning. We compute the corrected propagator. And then we go on-shell, if we want an S matrix, on the pole of the corrected propagator. Okay? So it's very useful to be able to imitate this program. It's very useful to be able to have a way of working off-shell to start with. In the end, you go back on-shell to get some effective deformation of these rules. But to understand exactly what you should be doing, it's very useful to be able to have a way, no matter how cumbersome and complicated, of going off-shell. This is what Ashok has been using again and again and again to great effect. Okay, the ability to go off-shell to define the correct procedures. Now, the off-shell quantities he calculates are not gauge invariant. But that's fine. In the end, he only wants to compute on-shell quantities. But he wants the correct rules for the computation of. So he goes off-shell in some non-universal way, then goes back on-shell, finds the answers finally are universal, but they give him the right rules. What are you really supposed to do on-shell? It's very beautiful, very complicated, but very beautiful. Okay? So I propose we stop this discussion now and go on. Maybe next semester we can come back to a more serious discussion. Is this okay? Great. Now, there's one last thing that I wanted to discuss before we go on to more formal issues. Okay. And yes.
So if I have the string if I imagine the string actually moving through physical space, right?
Yes.
The momentum would sort of be the direction along that it's traveling. Right?
Yes.
To have an oscillator along this direction, I already sort of know is meaningless, right? Because that goes into the diffeomorphism.
Yes.
Right? So I sort of know that my oscillator has to be normal to it.
Yes.
But then I have another direction that my oscillator should also be meaningless, because I have two directions of diffeomorphisms. So where's that second direction?
Yeah. So now you know when you're doing this,
Yes.
you are pointing just in space,
Yeah.
but there's also time. Those are the two directions, basically.
Yeah. Time like and
Yeah. So
longitudinal.
the only non-trivial ones are those that are orthogonal to that whole plane.
Okay.
Okay. Good. Great. Any other questions or comments? Okay. So now there's something else that I wanted to tell you about. I don't know if you remember, but do you remember that when we were discussing the BRST quantization, one of the things we saw was that every BRST exact state had to be null. Okay? And this was the proof. The proof was, suppose I compute psi q psi.
Because they are orthogonal to these physical ones.
They're orthogonal to physical ones, and therefore it's 0. But in particular, they're orthogonal to themselves because q squared is 0. We use here that q was BRST, that q was Hermitian. Q BRST was Hermitian. Okay?
Does this tell us that this is not really a Hilbert space?
What?
Because the inner product is degenerate, does this tell, like, is this a statement about this inner product not really being an inner product?
Yes, so you see the whole space that we're working in does not have positive definite norm. So let's study that issue. Okay, first there's something I should have said before we get into this, that at level 0, the state that we were looking at had a name. What was the name? I didn't say it last time. It was the tachyon. It was the same scalar particle that we found with mass squared negative, with the same mass square if you go back, alpha prime by 4, or 4 by alpha prime, in our light cone quantization. Here what we found at level 1, if we take 1/2 of it, is just a photon. But if we take the left and the right part, we get the group theory structure of photon times photon, meaning vector times vector. Vector times vector of SO24 is symmetric tensor, scalar, and antisymmetric tensor. Symmetric tensor is the graviton. Antisymmetric tensor is this field, this B mu nu field that we will encounter, Karl-Bramon field that we will encounter more and more as we go on. And the scalar is a very important field. It's called the dilaton. It will have something to do with the coupling constant of string theory. We'll go on. So in this bosonic string, we've seen that the massless sector consists of a graviton, an antisymmetric field, which we call B mu nu, the Karl-Bramon field, and a scalar, which we'll call the dilaton. Okay, now we go back to the question of the inner product on the space. Of course, this space does not have a positive definite inner product. That does not have a positive definite inner product. Let's examine that. Firstly, let's look at the matter sector. Let's look at alpha minus 1 mu times alpha m mu times alpha n nu. This is something we've computed many times. Okay, and we found that it was m times. Now when we go back to Lorentzian space, delta becomes eta, eta mu nu, and delta of m plus n 0. Okay. So let us look at the inner product that comes from this from that commutation relation, the inner product on these oscillator number -1 sector. Okay, so the oscillator number -1 sector, all our states were alpha -1 mu on down and k. This down k will play no role in what I'm saying, so I'm just going to call it 0. Okay, so I don't have to keep writing down k. Alpha -1 mu and 0. Okay, now let us take an E mu on this and compute its norm. Okay, so what I want to do is to compute 0, E mu alpha 1 nu E alpha 1 nu. Because the dagger of alpha minus 1 was alpha 1. Okay? How do I compute this norm? What? Epsilon, I was taking that to be real, but okay, yeah. Okay, so you're right, that if this is a complex, we could take it to a complex one. Okay, now let's take this alpha 1 through to 0 so that it annihilates it. So we use this commutation relation. So what do we get? We get alpha epsilon star mu epsilon mu eta mu nu. Okay, and then the remaining term is 0 because it goes through to the right and annihilates. Okay, where I've used the fact that here m is equal to 1. 1 was not important, but it was important, it was positive. Okay, so now on this 26-dimensional space of epsilon, so my space of states here, the path that I've been looking at, is 26-dimensional because alpha minus 1 mu. So I've got a 26-dimensional vector space. What is the inner product on that Hilbert space? These are the coefficient vectors. So it's coefficient times coefficient star, but with an eta mu nu. Had it been with a delta mu nu, this would have been a standard inner product. But we've got an eta mu nu, and eta mu nu has 1 minus 1. Okay? This already shows you that this is not a positive definite inner product space. Let's do the same with the BCs, with the BC system. Okay? So let's see, what were our states? Our states were B minus 1 on 0 and C minus 1 on 0. As usual, B minus 1 dagger is B and C minus 1 dagger is C. Okay, let's call this state B and let's call this state C. Now what's the inner product of B with B? Already looking bad. Okay, what's the inner product of C with C? What's the only non-zero inner product? The only non-zero inner product is BC is equal to CB is equal to 0. Is equal to 1. Where I use that B1C minus 1 is equal to 1. And also C1B minus 1 is equal to 1. Right? So if I want to calculate this guy, for instance, this would be C minus 1. This guy would become B1. I would take the B1 through, I would pick up this 1. So what's the matrix of inner products in this BC space? It's a matrix that is 0, 1, 1, 0. That's sigma x, which by a coordinate transformation, a basis change, can be made sigma 3. Okay, which is 1 minus 1s. Again, there's the minus 1. One of the eigenvalues is 1, the other eigenvalue is minus 1. It's because there was a minus eigenvalue that you could have had a null state. Okay, here also, because there was a minus eigenvalue, you have null states. What are the null states? The null states are states in which this epsilon is null. It's a null vector.
Or time-like.
Well, time-like will give you a negative norm state. But the zero norm state
0 is null.
is the other null ones.
Sorry.
Okay? So we've got this inner product here. In this 28-dimensional space, can you see that the inner product matrix has 2 negative eigenvalues and 26 positive eigenvalues? If we diagonalize the inner product matrix. Now we've just done it, right? This is eta here, and it's this. Yeah. So it's 26 pluses and 2 minuses. Okay? So this whole space is not a Hilbert space with a positive definite. But that's the whole point. We're doing this whole BRST procedure because we want to narrow down on the physical part on which the inner product should be well defined. Okay, so now let's say that we've done that here. Firstly, our conditions were that things had to be BRST closed. Okay, the BRST closed condition was that k dot epsilon was equal to 0 and that the coefficient, that we're not allowed this B state. But we still have 26. We still have 26 dimensions in a Hilbert space. What is it? It's epsilon dot alpha minus 1 plus zeta times c minus 1 on 0. It's exact. It's exact. But at the moment, I've just thrown away the things that are not closed. That's why. Now I want to check what is the inner product on this space of things that are closed. Okay? On the space of things that are closed, what kind of inner product do I get? Well, suppose I move to a Lorentz frame so that k mu was equal to 1, 1, 0, 0, 0. Okay? Everything that is orthogonal to k is either in this direction or is equal to k. So there is a basis for these guys such that E is equal to EI, that's the orthogonal guys, orthogonal to the momentum, but in this space orthogonal, yeah, plus EI mu plus, E perpendicular, let's call it, 24 of these, plus K mu times alpha. So this is the 25-dimensional basis of this part, 24 plus 1. And here we had. Now on this space, let's take alpha minus 1 mu, and zeta. On this space, let's compute the inner product. What do we get? We get E perpendicular mu star E perpendicular mu. And that's it.
Why are you bothering with the k mu part? You can throw it away.
Right, but I want to show you what happens before I throw it away. Suppose I take the space which includes the exact pieces, and on that I compute the inner product. Okay? Yeah, sorry. I keep to the closed sector and compute the inner product. Now I've got a 26-dimensional space, but can you see what the inner product becomes? It becomes just E mu perpendicular star E mu. Why? This dot itself is 0 because k squared is 0, and this dot this is 0 because it's perpendicular. What about c minus 1? Clearly c minus 1 is 0 dotted with anything here, and c minus 1 is 0 dotted with itself because c with c was 0. So now what is this? What is the signature of this inner product? 24, 0, 0. Okay? The full guy had 26 ones and 2 minus ones. Once we restrict to the space of cube BRST closed, we have a 26-dimensional space with 24 ones and 2 zeros. Okay? Now, what is the space of zero norm states? Clearly, it is zeta times c minus 1 plus alpha times k mu, because these are the things that don't appear in the inner product, times alpha mu minus 1. And these were precisely the BRST exact states. This will be a general thing.
You've given an example that when you have BRST exact thing that has 0 norm.
0 norm, we already knew that.
And you have given an example.
We've just seen that in particular. But what we are seeing more, that's more important, is once we throw away these BRST exact things, the inner product is now positive definite. This is the whole point of the BRST procedure. To remove the junk so that once you've removed it, now you've got a good unitary theory. Okay? Great. Okay, now that we understand this level 1 stuff in some detail, now we're going to go and behave more like mathematicians and try to find an abstract proof of what is called the no-goes theorem. Okay, so let's see how that goes. I want to show you, I want to completely characterize, not just at level 1, but every level. I want to completely characterize the BRST cohomology. What I mean by that you will see as we go. I want to give a human understanding of the BRST cohomology and also prove what I just showed you. Prove two things, namely that A, the BRST cohomology, that once we restrict to physical states, the inner product is positive definite. And B, that the BRST cohomology is a one-to-one map, is in one-to-one correspondence with the light cone gauge Hilbert space. And something else, which we'll come to as we get to it. Okay, this is what I want to prove. And unlike most physics arguments, you start from some place whose relationship to what you actually want to prove is not so obvious until you get there. This is a mathematics style argument, so I'm going to go through it. Okay, so the hero of the story is of course the BRST operator. And what we're going to do is something a bit strange. You see, the BRST operator is hard to work with because it's such a complicated operator. So what mathematicians like to do when they're faced with something complicated is to simplify it, capture the essence of the problem, and then upgrade their proof to the complicated thing. Again, that's what we're going to do. It's a standard strategy while dealing with cohomologies, which is much studied in mathematics. Okay, the first thing we're going to do is to define this quantity. I'm going to define this quantity which I'll call n light cone. I'll make sure my definition agrees with Polchinski. Okay, the first thing I do is the following. I choose two directions in space-time, let's say 0 and 1.
So what was the commutator of C1 B minus 1 1?
Yes. Yes, anti-commutator. Yes.
Sorry.
No, yes. Choose the 0 and 1 directions in space-time as special and make light cone coordinates out of these 0 and 1 coordinates. Okay? Yeah. So I'll define everything carefully. Let alpha plus minus equals 1 by square root 2 alpha m plus minus alpha 0 m plus minus alpha 1. Okay. This is clear. It's just linear combinations of the creation and annihilation operators of 0 and 1. Okay. Now the next thing we do is to remind ourselves of the commutation relations of these alpha plus minus. Okay. So we have alpha plus minus m alpha minus plus n is equal to m delta of m plus n 0 to the minus sign, I believe. Yeah, let's check this. So suppose m was positive and n was negative. Okay. Now the alpha 0 with alpha 0, see, we'll get a half because the 1 by square root 2 will be. The alpha 0 with alpha 0 would give a negative because it's 0. So the commutations are opposite to what they are for the space. Remember that the commutation relations had an eta mu.
Z plus minus is something. Is it minus 1?
That's a matter of convenience. Yeah, exactly. But just look at it. Just work it out. 0 with 0 will give you minus. Yeah, you're right. It's just that g plus minus. But we don't have to get into that. 0 with 0 would give you a minus because it's just the opposite of what we normally get. And 1 with 1 would give you a plus, but here we're doing 1. On one side we've got a plus. Exactly. Okay? So both of them become minus, and then we get a minus. Okay. Fine.
So in the same speed it is light quantization, therefore expression for t will become same thing probably, and that, so your qb will be related to t, so that will slightly something.
Yes, but we'll do something more than that. Okay. Now the next thing I do is to define a charge, which is called NLC, number in the line code direction. Okay, and this is defined as, and of course I've not written that commutator of plus with plus and commutator with minus minus is 0. This you know, right? Okay, NLC is defined as sum over m 1 by m alpha plus m alpha minus m minus. Okay.
But how is a negative? Is it always negative or always positive?
Well, it could be both. Let's check. Okay. You see, let us see what this does. This sum over m, I first should say, is m not equal to 0, but otherwise runs from minus infinity to infinity. Okay? And this sum over m is therefore runs over positive and negative. So let's separate into positive and negative. Okay? So this thing is equal to, and I suppose this is
Normal
oscillator
order.
minus plus oscillator number.
yeah.
Minus minus plus.
Yeah. Yeah, and this whole thing is going to be defined as normal order. What?
It is minus oscillator number minus plus oscillator number.
Exactly. Let's see that.
Because you didn't put a minus sign.
Because
There is a minus sign there. So it got
exactly. So look. So let's separate this into m from 1 to infinity and m from minus 1 to infinity. Okay. So this is m is equal to 1 to infinity, 1 by m. Okay. Alpha m plus alpha. Since it's normal order, we always put. In this case, I just mean oscillator normal ordering. Just pluses to the right. Okay. So alpha minus. So let's see. Minus m. So I wait. So I want m is equal to 1 to infinity. So alpha minus of minus m, alpha plus of m. But now we're going to get a minus sign, because when m runs from minus infinity over negative numbers, this comes with a minus sign. Okay? So minus alpha plus minus m, alpha minus m. Now this is m is equal to 1 to infinity. Is this clear?
Why do we have the pluses to the right in the second term?
Because it's always the pluses to the right. That's what normal ordering means. Okay? Now, let's act on a state. Remember that that this 1 by m just is absorbed into the non-standard commutation relations of these guys. That's the m in here. Okay? So what does this do? Suppose I had a minus oscillator, an alpha minus of minus k, say. This guy, suppose I had a plus oscillator, because minus kills plus. Okay, suppose I had a plus oscillator of alpha plus of minus k. So suppose I act with this alpha plus of minus k. Okay, This term on that would be 0 because the alpha pluses just go through. This term on it is not 0, but it picks up a minus sign because of this minus 1. Okay? So we would get a factor of plus for that. On the other hand, suppose I had a minus oscillator, alpha minus of minus k. This term would be 0, this term would be non-zero, but we'd get a minus for it. So what does it count? It counts the number of plus oscillators minus the number of minus oscillators. Okay? So what is this NLC? Number of plus minus number of minus os. And now, I'm sorry, irritatingly enough, I've messed up. I mean, I put the minus sign from Polchinski. Polchinski defined this plus. I'm sorry. So everything here will come with a minus sign. Okay. It doesn't matter at all. But let me level. I'm sorry. This will come with a relative minus sign. So with plus and minus. Okay. And so it will count number of minus number of plus. Sorry about that. Okay, this definition counts number of minus number of plus. I just want to stick to Polchinski's notation so that we can use his arguments without change. Okay, so we'll remember what this is. We'll keep this on the board. And this is, yeah, it's this quantity. Maybe we keep this on the board as well for a while. Okay. Now, next question, does the BRST operator commute with NLC? That is, does the BRST operator carry NLC equal to 0? Almost, right? Because what is NLC very close to? There's a conserved generator that NLC is very near to. What? It's almost.
Charge in this rotational plane.
Yeah, it's almost the boost generator in the 0, 1 plane.
Because it's a 0 and
0 and 1, otherwise a rotation, right? Almost that. You see, because what it's doing is counting the number of, in the 0, 1 plane, a plus oscillator has charge 1, a minus oscillator has charge minus 1. So it's counting the oscillators with charge.
Why did you say almost?
Almost because m not equal to 0.
Okay.
Oh, but it's very important. Okay? Because there are also 0 modes in the story. Okay? The real generator of Lorentz transformations of boosts will also include 0 modes. Okay. Now, had it been that this NLC was the full generator, including the 0 modes, then QBRST would have commuted with it. Because QBRST is Lorentz invariant. Okay? But it does not include the 0 modes. Okay? And so for that reason, QBRST will not quite commute with it.
Only the 0 mode part.
Only the 0 mode part will survive. So now, in order to proceed further, I want to develop this expression for QBRST in terms of oscillators that I promised we would do last class, that I should have done before doing the painful calculations of last class, would have speeded it up. But I want to develop that representation, and then we will see, many things will become transparent. So let us remember, JBRST was equal to what? Was C times T plus, somebody help me, what is it, B C del C? Am I getting my signs right? Can somebody look up or shall I? They're all okay? Okay, great. Now, okay.
Okay, now you will say this sentence. Oh, sorry. Now this 3 by 2 del square C is important sort of in the sense that if you do not put this, you said this will not transform nicely.
Yes.
And because of you have proved this, so this is Lorentz invariance is sort of related to this.
Maybe in some deep way, but not.
Lorentz invariance of the current JB. It will of course not affect physics.
No. This is Lorentz invariance, not in the two-dimensional space. In target space.
Yes, yes. If you are in 0, 1 plane in space time.
In space time. So this del square C has nothing to do with it. Yes. Yes. Okay. So let us keep going. So what we want to do is to remember our expansion. C was equal to sum over m, Cm by z to the power m minus 1. B was equal to sum over m. Okay. Bm by z to the power m plus 2. And T was equal to sum over m, Lm by z to the power m plus 2. Okay? What I want to do is, and finally QBRST was integral JB or if you want, I could have taken JB and expanded it in a similar way. JBRST m by z to the power m plus 1 because it's dimension 1. And J0 is QBRST, which would have been the same formula as this. Okay, these are equivalent statements. Okay, so now what I'm going to do is the following. What I'm going to do is just plug these expansions into here, into this formula, and work out an expression for Q in terms of these oscillators. What is the danger in this procedure? The danger in this procedure is that we're not taking care, I'm going to act as if the oscillators were classical. So I can move the orders around at will. Well, the normal order is true, but what I'm going to do is to oscillator order them.
So we just have to care about the zero. Oh, that's all we're seeing is a zero.
Well, but you're right. Let me say more clearly. What I'm going to do is to take an expression, and then every time I get something, I will just order the oscillators in oscillator normal ordering. This may be wrong, okay? But we'll identify the possible mistakes we've made, and then we'll fix that by a more sophisticated argument. Okay, so first thing I'm going to do is to do a crude calculation without worrying about possible ordering ambiguities, and then I'll use something more sophisticated to fix that. Is this clear?
Q is dimension 0 operator, so everything comes with m comes with minus m.
Everything comes with m comes with minus m, but for instance, between C and T, there's no ordering ambiguity. It's only a question of when there's an ordering problem, because C commutes with L. So there'll be only very few ordering ambiguities. Only from here. We'll see.
C and T are the two different sectors.
Two different sectors. Here this is linear, so there's no ambiguity.
Those should not play a role, so then
It's only between B and C. But you see, when there's an ordering ambiguity with B and C, it'll give rise to a potential ambiguity to a term that's linear in C. So we'll parameterize the potential ambiguity and then fix that by another argument. Okay, so it's almost completely determined up to without any ambiguities. Then we what could the ambiguities possibly be, and then fix it. Okay, so but first go ahead doing it naively, then we'll worry about the ambiguities and fix that. So go ahead doing it naively is of course very straightforward. All we have to do is to put this expansion. So let's do the first term. Cm1 by z to the power m1 minus 1, and then Lm2 by z to the power m2 plus 2, and then we want dz. But clearly this just picks out the pole, so it picks out the terms where m1 plus m2 is equal to 0. Okay, so we get some Cm L minus m, and that's it.
Yeah, this is dimension 0 operator, you just have to couple.
Exactly. But it comes with these coefficients, with coefficients 1, if you're interested in that. Okay, now let's look at this guy, because that's also very easy. Okay, so this guy, which of course won't do much, but anyway, I have to act with two derivatives. First derivative will make the z to the power m, and we'll pick up a power of minus m. Minus of m minus 1. And the next derivative will make it z to the power m plus 1 and pick up a power of minus m. With the plus now. M into m minus 1. So we will get this times sum over m Cm by z to the power m plus 1. I should put the sum over m outside. We pick out the pole. So we just get m equals 0, but that comes with an m. So that gives nothing. Okay, so forget it. This was, of course, the fact that this did not contribute to the charge because it was a total derivative. It's obvious, right? We're taking j integrated over z. This is a derivative. It's not going to contribute. Okay. Now, finally, we get the most complicated term. The most complicated term is from here. So what do we get? So we take bm1 by z to the power m1 plus 1, plus 2. Cm2 by z to the power m2 plus minus 1. And now we get a minus of m3 minus 1 Cm3 divided by z to the power m3. Good. So firstly, what do we get? These two, we have to keep track of this index separately.
Yes.
Okay? But these two just come together, they just care only about the net power of m. Okay? So let's write it as, okay, firstly, at the gross level, the coefficients of this have to add up to what? 0, because 2 minus 1 is 0. Okay? So we have to have delta m3 m2 m1 plus m2 plus 0. Then we get a minus m3 minus 1, and we get bm1 cm2 cm3. I mean, that's one way of writing it. But another way of writing is to use this to do the sum to fix what m3 is.
But we also need that M2 can't equal to M3, right?
What?
M2.
M2 can't equal m3. But we won't put that in explicitly. If we get a term, it just is equal to 0. Okay? So a simpler way to write this is to do the sum over m3. So m3 is equal to minus of m2 plus m1. So m3 is minus of m2 plus m1. So this will become m2 plus m1 plus 1. B m1 c m2 and c m3.
And sum over m1 and m2.
Sum over m1 and m2.
Also, m3 you don't write as minus m2 plus.
You do write that. Thank you. Minus of m1 plus m2. Okay? We will operate a normal order this. So put everything to the right. And what are the only ambiguities? Well, the only ambiguities can happen when one of the b's is equal to the coefficient of one of the c's with a minus. But the sum has to add up to 0. So the only potential ambiguities occur with the C0. Only potential normal ordering ambiguities are terms proportional to C0. Because a B has eaten up a C and what remains has to be 0. Okay. So up to ambiguity of, okay, I'm going to ask you guys for help with these formulas if we need them, so I can use them.
Why do you say it has to add up to 0? I'm sorry.
Well, the whole thing adds up to 0, but these things go through each other unless B plus, let's say, look at this with this. There's ambiguity in ordering only if this plus this is 0. So there's some ambiguity in the ordering of this and this if this plus this is 0, but at that point this has to be equal to 0. Or there's some ambiguity in ordering if this plus this is equal to 0, but at that point then this has to be 0. Right, because the sum of the three indices is 0.
So if one of the C's are 0, basically.
One of the C's has to be, so only terms with one of the C's being 0 is ambiguous. Okay, so there's only one number that's ambiguous. That's pretty impressive. I'm going to appeal to you for help if we need these formulas again. Okay, so what we found now is that QBRST is equal to sum over M CMLM, every operator normal order, okay, plus sum over M1 M2 M1 plus M2 plus 1 BM1 CM2
L minus M, L of minus M, right?
Thank you. C of minus of M1 plus M2 operator normal ordered plus A, something I don't know, times C0. All good? Naively it will be infinite, but of course.
Because there is this derivative term will have a m.
Yes. So it's the usual thing, right? It's this 1 plus 2 plus 3 plus 4 gives you minus 1 by 12. You have to find what is the thing that is consistent with our operator algebra. How am I going to do it? So instead of trying to regulate and so on, I'll be clever. And the way I'll be clever is to find a commutation relation that we've deduced from operator identity.
0 times that one.
Exactly, exactly. This is sensitive to B0. You take the commutator of this with B0, you get an A. But we know that QBRST times B0 is equal to L0. Okay? So, by using this, we can fix A. How would we do that? Actually, it's a little, because I haven't done this oscillator business. First thing is you have to find L0, of course, in the matter sector is very clear. But what is L0 in this operator language in the ghost sector? You have to do this exercise again. Okay? But the normal ordering coefficient in the ghost sector was very clear because, okay, let me at least schematically do that for you. What we have? We had B del C minus 2 del of BC. Have I got this right? B del C?
So del BC.
Was it del BC? Sorry. Del BC. Thank you. Del BC minus 2 by minus. Now once again we plug this in. And what I want is an operator relationship for L0 in the ghost sector. There's a potential operator ordering ambiguity. That potential operator ordering ambiguity will be what? Only if a BM hits a C minus M, and then what will be left over? Identity constant, right?
Yes,
right? So when we work this out, using similar, okay, let's just do it. Okay. I was going to say you can do it yourself, but let's just do it because we've not done this calculation. Okay. Shall we do it or will you? You'll do it. Great. Everyone's happy with that? What I mean is, you'll get an ambiguity with a constant, and you fix that by knowing that the vacuum has L0 equals -1. So the constant is -1, because once you've normal ordered, it annihilates the vacuum. So the constant will be -1. Okay? So you get some relationship here. You get some formula for this thing doing operator normal order, including a -1. Okay? But that formula has to come out from here. And if you work that out, you'll find that this has to be equal to -1. That -1 has its origin in this -1. I haven't worked out the algebra because it's a bit painful. But
You just calculated L0 from this expression.
I just calculated by using the same procedure.
And then said that L0 acting on the vacuum is -1.
And then the normal ordering thing is just a number. We fix the number by knowing that it's -1. Okay? So you get some answer. Then you do this calculation using the oscillator algebra. You do the calculation using oscillator algebra. Okay? And if you do it carefully, of course, you will get L0 plus a constant. And you'll choose your coefficient of A to make that constant the same normal ordering constant that appears in L0, that is just L0. Okay? So it's conceptually very simple. It's a bit painful to do, so I won't, unless somebody wants it. Okay.
In general, you find this commutator of L plus 1 minus 1, and then you say that this algebra has to satisfy, and
that will also determine the constant. That's correct. That's correct. So we could do it more abstractly without using that the vacuum is -1. Yes, we could do that way as well. Okay. But when you do that, you'll get this answer. Let me just check that this M1 plus M2 plus 1 is what Polchinski has. Now, I'm very sorry, but Polchinski doesn't, well, let me just report it the way he does. Let me just report Polchinski's answer and then we'll track down a mistake, sorry. He reports it as Cn B of minus of M plus N and proportional to M minus N by 2. Oh, maybe it's the same. And then he sums well, firstly, there's the 1, but maybe that disappears because 1 probably disappears because well, firstly, has this we have this 1, and secondly, has this by 2. Well, how did we mess up so badly? Just give. By 2 from. Give me, maybe we should get this straight because the details might, well, actually it won't matter for the no-goes theorem, but we should get it. We should get it straight. Just how did we mess up so badly? So give me 1 minute. B C del C. That looked okay. The M minus N. It's just the C's. Is that right? Let's see. Let's rewrite this as a sum where the indices are on the C's. Okay, and let's see what happens then. Okay. So let me write this as sum over. I'll call this. I'll follow his things. So he had Cm and Cn. So let me call this guy M and this guy N. Okay. So firstly, what is M2 plus M1 plus 1? Okay. That is, as you say, N plus 1 minus N plus 1. The whole thing in here we'll call N. Right, so minus of M2 plus M1 is N. So that's minus of N plus 1. And what is this M1?
This is 2. Minus of N plus 1.
Minus N plus 1.
Whatever is written here, yes.
Oh, it's right?
Yes. No, M minus N by 2 is 1 minus N. But I don't know how it will be M minus N by 2.
Let's just go through it slowly. Yeah. So we had, I want to know what is M1. So N minus M, right? N. Sorry. Yeah. M minus N.
Just charge conservation. B of minus M plus N.
Yes.
M plus N. And minus.
Minus and minus.
You're right.
You don't calculate this. B of minus M plus N.
Cm, Cn. Yeah, you're right.
Yeah, there's plus sign in between.
Yeah, you're right.
It's just 0. You want to add up to 0.
Yeah, you're right. You're right. You're right.
Don't do the algebra.
Yeah. Okay, and this N was okay. Now, you see, the sum over 1 will give you 0 because Mn and Nm will cancel. Let's take the term with the 1 here. See, the whole expression here is antisymmetric in M and N. Unless the coefficient here is antisymmetric in M and N, you'll get 0.
Yes.
So the one piece here will give you 0. And for the same reason, we can replace N with N minus M by 2. Okay, which is M because of the minus sign. So, okay. The sum over M minus N by 2, Cm, Cn, B of minus M plus N. Okay, good. We went through. It's just that he found a more elegant way of representing it. So we'll write that there. Antisymmetric, and that was the point. Okay, and minus is here. Okay, good. So now with this in our hands, let's go back to the calculation we wanted to do. I will also write down here NLC was equal to whatever it was. NLC was equal to 1 by M alpha minus alpha plus of minus M alpha minus of M. which is equal to number of minus minus number of plus. Excellent. Okay. Now, with these in hand, I'm going to ask what, you remember the question we started asking to get into this? The question I'm going to ask is, what is the charge of Q under NLC? Now see, in LM, okay, in LM we have terms which are alpha minus m, alpha plus m. So LM goes like alpha minus m, alpha plus minus m, or plus minus m, or with some m's and so on. That doesn't matter. Sorry, in LM we will get with a plus m. Yeah, m plus n and alpha minus n. Okay, but the important point is that all such terms, okay, have charge 0 unless they involve an alpha 0. Can you see this? Of course, it had to be because it was just the Lorentz generator. But let me we could calculate this if you like, right? We just want to take the just put the commutator of this object with this object. Just the fact that it has as many minuses and as pluses. Okay, we'll make it 0 unless it has an alpha 0. Notice that an alpha minus with a negative index creates a minus oscillator, but an alpha minus with a positive index destroys a plus oscillator. So alpha minus modes, whether positive or negative, all have the same charge. Did you see that? Let me say it again. What is this charge counting? Counting number of minus oscillators minus number of plus oscillators. Now let's take an alpha minus k. If k is negative, it creates a minus oscillator, so it increases NLC by 1. If k is positive, it destroys a plus oscillator, and so it also increases NLC by 1. Okay, so the NLC charge of any object is simply number of minus oscillators minus number of plus oscillators. Is this clear?
It's a number of minus objects.
Minus objects plus number of plus objects. But we're not supposed to count the objects with index 0 because those aren't there. Okay? So the generic term in LM will give you charge 0. The only term that will not give charge 0 is a term with an alpha 0. Is this clear?
Alpha plus of negative creates alpha plus.
Alpha plus of negative creates alpha plus, yes.
So NLC contribution gets a minus 1.
Correct.
And alpha plus positive destroys a negative oscillator.
Yes.
Therefore, that also gets a minus 1.
Yes. So all alpha plus objects have charge minus in this case, but okay. Okay. And all alpha minus objects have charge 1. So unless there's a 0, it's neutral. So the bulk of the operator is neutral. But you see there is a term where either the alpha minus is 0, in that part will have charge minus 1.
You should not, is this statement correct? This was a space-time symmetry,
Yes.
which has nothing to do, this M and A, all these things is wall sheet stuff.
Yeah.
This was a space-time symmetry and we are calculating charge around that. So it's the upper things is what matters.
What?
Upper sign is what matters.
Upper sign is what
You
matters.
can just forget about dot sign when you are calculating the charge with respect to this charge.
That's correct. That's correct. That's correct. That's correct. But you can see it physically.
Yeah. It's just, that has nothing to do with wall sheet. What
Correct.
something.
Yeah, that's absolutely correct. Exactly. Okay, so you see the term with an alpha minus 0 will have charge minus 1. The term with an alpha plus 0 will have charge plus 1. Because the term with an alpha plus 0 will carry no charge from here, but carry charge 1 from here. Okay, the term with an alpha minus 0 will carry no charge from here, but carry charge minus 1 from here. So you see that QBRST can be written as Q1 plus Q0 plus Q minus 1. Where Q0 has most of it, but Q1 is very simple. Q1 is the charge with alpha plus is 0, and therefore is Cm. This is 0, so that's alpha plus 0. Alpha plus is proportional to K plus. Yes. Some 2 alpha prime or something like that, but doesn't matter. K plus Cm and alpha minus of m sum over m. M is equal to and this should not go over this guy equals 0. So m not equal to 0. What?
Signs do not aim and minus. What happens?
I'm sorry. One of them is a mix. Yes. Is this clear? Okay, now I'll just check. Overall number I've not been careful about. Pulchinski has, I'll put it right. Minus, not that it'll matter for anything, but Q1 is equal to minus square root of 2 alpha prime K plus. And he writes it as alpha minus m, Cm exactly as we've written it. M not equal to 0, otherwise m runs from minus infinity to infinity. Okay. The term with m equals 0 would belong to Q0 because both were 0 modes. Okay. Similarly, that's Q1 and Q minus 1 has a similar expression. You just flip plus and minus. Okay. Now, what we see is that Q minus 1 is a very, very simple operator. Right? For instance, it's quadratic in oscillators. Okay?
What was an alpha plus 0? That was neutral under this symmetry.
What? It was neutral under the symmetry we've defined because NLC has no m equals 0 component.
Okay. Okay, sir. Yeah, that doesn't the definition.
Right. Had we defined it including the 0 mode, it would not have been useful. We want to isolate a part. The whole point is to isolate a simple, interesting term. You see what we do with it. This is a mathematics style argument, right? It's only at the end that you see why you're doing what you're doing. Okay? Great. Let's move. Now, the problem we're going to set ourselves as a trial problem, and then we'll soon see we can upgrade it to the real problem, is to compute the cohomology not of Q, but of Q1. Firstly, does this question even make sense? Well, let's see. We know that QB squared is equal to 0. And let's just put in QB is equal to Q1 plus Q0 plus Q minus 1 and open out that equation.
Just from charge concentration it has to be 0.
Exactly. So what we will get is QB squared is equal to, not even conservation, just the fact that you can act on sectors of the Hilbert, that you can diagonalize the Hilbert space. There's no dynamics here. QB squared is equal to Q1 squared plus, now this is the sector with charge plus 2. In the sector with charge plus 1, we'll have Q1, Q0 anti-commutator. Plus in the sector with charge 0, we will have plus Q0 squared plus Q1, Q minus 1 plus q minus 1 q 0, it's charge minus 1, plus q minus 1 squared. Right, I've just written out in the charge sectors under NLC. This is equal to 0. Now this is 0 as an operator. So take your Hilbert space and break it up. Break up your Hilbert space into sectors of particular NLC charge. Each has to be independently 0.
So let's look at the charges, right? Q1 squared is 0 for that reason.
Yes?
Q minus 1 squared is 0 for that reason. The complicated part is in the middle.
In the middle, and that has to be 0 as a sum. We won't use that. We don't care about that. We just want to we'll use this equation to show that q1 squared is equal to 0.
That one for charge conservation.
Because of charge conservation. In each charge sector, it's 0. Right? Right? We take the commutator of this with NLC, for instance. You get, but you're taking the commutator of 0, so you'll get 0. Then each of these will have to be 0. Okay? So what we've concluded is that q1 squared is equal to 0. Because it's 0, it's separately in each charge sector. Right, you take 0, you take the commutator of it with NLC. It has to remain 0. But the commutator with NLC is different in different charge sectors. Therefore, each has to be 0. Do you understand what I'm saying?
I think so.
I'm saying that suppose I've got an operator with charge, some operator which is sum over AM QM, where QM is some charge under some other operator. And I know that it's 0. Okay, let that other operator be n. Okay, so this is equal to 0. So n commutator 0 is equal to n commutator 0 is this q is equal to 0 because q itself is 0. Okay, and therefore for each qm individually it's 0 because you get different numbers behind each of these.
Like you have a differential equation to solve, and then you have a global symmetry.
Yeah, it's the usual thing, right? You've got an operator with different charges, different paths phase differently. They've got to be 0 before and after phasing. They each individually have to be 0.
Individually have to be 0, and clearly then you have found that kind of operator.
Yeah.
You have found an operator which is NLC.
Yes.
Which is the creative.
Okay.
In general, it will be proportional to identity.
What?
Why 0 only? Any commutator identity is also 0.
No, you have the whole thing. See, this operator. See, we've got an operator that's got to be 0. Now you phase it. You take each part of it and act with this generator. Each part of it changes with a different phase, and the sum after phasing has to also be 0. How can that work unless the parts that change independently with different phases are 0? You know, it's like, okay, you've got a vector, it's 0, all its components have to be 0. That kind of thing, right? The part with 0, angular momentum 0, angular momentum 1, angular momentum minus 1, all independently have to be 0. Okay. Okay, great. So we've got q1 squared is equal to 0. Now, because it's an operator which squares to 0, the question of computing its cohomology is well defined. Okay, so because it's an operator whose cohomology is 0, by the way, if you could also just explicitly check that it squares to 0, right? Because the anti-commutator of this operator with itself is 0, because it has only C's and no B's, and therefore it's 0. Okay, so you don't have to be this sophisticated if you don't. But we've got an explicit expression, you can just check. Okay, now because this q1b squares to 0, the question of computing its cohomology is a well-defined one. Okay, Now we're going to compute its cohomology, and we're going to use a standard trick in mathematics to do that. And that standard trick is this. When you've got an operator of this form, it's basically useful to consider, well, the dagger. But the dagger normalized usefully. So consider the operator, I think Polchinski calls it R. R. Consider the operator R, which is 1 by square root of 2 alpha prime k plus sum over m alpha plus minus m and now b m. Okay, it's an operator that is chosen so that it will have, okay, well, this is our definition. Now, why have we chosen R and Q1 like this? We've chosen it so that because of the following. Compute now Q times R. Okay, let's do the calculation. Firstly, the square root 2 alpha prime k plus, that cancels. That's the normalization. So this is equal to minus of the anti-commutator of n not equal to 0, Cm minus and alpha minus m, sorry, Cm and alpha minus m minus, and n not equal to 0. Okay, n not equal to 0, alpha plus minus m, bm. I've just written down what the terms are, and the minus was, well, because this had.
Analogy for this is input matrix. In finite dimensional universe, what is this? What is this going on? Suppose you have some matrix which will take some times and then it goes to 0.
I didn't understand. Say again.
Sir, there are nilpotent. This is a particular kind of nilpotent operator.
You're looking at Q?
Q squared is 0, which is a particular kind of nilpotent.
Yes.
In finite dimensional Hilbert space.
You want an example of a nilpotent operator?
Yes, in finite dimensional Hilbert space, give me an example of nilpotent operator.
Sigma plus.
Sigma. If I try to find its cohomology,
Mm-hmm.
then what will be the analog for these two?
Let's work that out.
All I am trying to keep it in.
Yeah. Let's see. So sigma plus has the property that it raises spin. So Hilbert space is 2-dimensional. Okay. So you'll have sigma plus. In this case, it will be a trivial, but you see, you'll have sigma plus on down is equal to up, and sigma plus on up is equal to 0. So up is okay because it's Q closed, but it's Q exact. Okay. You'll want something less trivial.
But what was this? I just want to see the analog. What is R?
Huh. But yeah, but if you had a 0, see, suppose you had you want to see the analog. Okay. But first let me give you an example of something that will give you something non-trivial. Suppose you have sigma plus and 0.
Is it sigma plus that is here? R is sigma plus or not?
It's basically like a dagger in some sense.
This is sigma plus.
What?
If it's a dagger,
Like
it would be
this sigma plus. Is it that R is like sigma plus?
If Q is like sigma plus, is R like sigma plus?
R is like sigma minus.
Sigma minus. Yeah, probably. Probably sigma plus, sigma minus is some sort of identity kind of thing, except that it's 0. Yeah. It'll probably be that.
One of them is doing the homology, the other one is doing the co-homology.
Yeah. You see, in this thing we have sigma plus and 0, and the whole cohomology will be in the 0 sector. right? Because we've seen here that you get nothing.
You get nothing.
Yeah. Whereas in the 0 sector, well, that's in cohomology because Q1 something is 0 and anything there is not Q exact because Q just acts as 0. So the 0 part is sort of like everything. Okay, and we'll see something very similar happening here. So this sigma plus sigma I will give you R, which is identity. Yeah, so it will be very similar to this. Yeah, R will be like sigma minus. Yes. Will be like sigma minus 0. Okay, more precisely, there could be many sigma pluses with different numbers here. And R will be, yeah, it will just be the dagger. Basically be the dagger. With dagger in some space. Anyway, yeah, it will be like sigma minus, as you said. Now I want to do this calculation. Okay, so I get 4 kinds of terms, and we have to keep track of signs carefully. Right? You get the terms where these two contract with each other, or this and this contract with each other. Okay. Okay. I'm just going to write down the answer. Okay. So that we. Okay. We get sum over m b minus m c m plus c minus m bm minus alpha plus minus m alpha minus m minus alpha minus minus m alpha plus m. Okay, some straightforward algebra. Just open that whole thing out. Okay, and use definitions, or use the rule that the usual thing, right? Commutator rules, whatever. Okay, just open it out, some straightforward algebra, you will get this. Okay, now this we're going to interpret. Correct. Q1 has a definite. Yes.
Q1 has a definite NNC charge.
Yes.
Which is 1.
Which is 1.
R has charge what? Minus
0. Oh, R has minus 1 and this commutator has charge 0.
Commutator is only 0.
Yes. R has charge minus 1 because this is with pluses.
Because this is the dagger. Okay.
Exactly.
Sorry.
Exactly. Okay, now we want to interpret this. So look at this quantity. This quantity here is, suppose we count B oscillators and C oscillators, okay, weighted by their level, just like we count the matter oscillators. Okay, this quantity is, well, I'll write it without the weighting, N Bm plus NCm plus N plus M plus N minus M. M is equal to 1 to infinity. Okay? The charge that counts the number of B oscillators weighted with level plus charge that counts the number of C oscillators weighted with level, plus number of positive oscillators weighted with level, plus number of negative oscillators weighted with level. Okay. This is sort of clear. So, for instance, let's look at this term. This Cm. Okay. Now this here. Had m going from 1 to infinity. So any time that you had something the other way around, you reverse the order, Okay, so this Cm here destroys a B oscillator and creates it again. So this quantity counts the number of B oscillators weighted with M. Similarly, this quantity counts the number of C oscillators weighted with M. Okay, now both these quantities count the number of plus or minus oscillators because of the minus sign and the minus sign in the commutation relation. So this quantity counts the number of plus oscillators weighted with M. It's weighted with M without, even though it doesn't have this explicit M, because the oscillator normalization has M. And this quantity counts the number of minus oscillators. The fact that these were minus was related to the fact that the commutator had a minus. That's why it was this counting thing. Notice, and this is really important, that each of
M is multiplying others. Oh, M is coming from the commutator, right?
M is coming from the commutator of this and this.
But B and C, this commutator
Did not have an M, and therefore. Okay, notice that each of these is a positive definite operator. That is totally crucial.
That had to be because you have taken Q dagger kind of anti-commutator.
Yes, but it's very important that it's a sum of positive definite operators.
Oh, now all of them will be zero if it is zero.
Exactly. Okay, M is a positive object, and it's sum of 4 positive definite operators. Okay, so this whole thing has been cleverly engineered so that this happened. Now we're going to start the argument. Okay, now that we've gone through the algebra, we have no algebra left, I think. Now it's just thinking. Okay, so we want to kind of compute the cohomology of Q1. Okay, so the first thing I do is this. Let this thing be defined by S. Okay, now notice that Q anti-commutator S. Go on.
First of all, I wanted the singlet sector because let's say my goal is to get some number operator kind of thing which will be positive definite.
Mm-hmm.
Then first I noticed that any number operator will be singlet under this. So I want singlet kind of object. So I get Q and Q dagger. And then I took anti-commutator because anything that passes through each other like matter and ghost, they will not click. So it will end up giving me something like that.
Yeah, you want to get a bunch of quadratic expressions. You've got quadratic, you do Wick's theorem, so you're going to take an anti-commutator. You have to adjust things so that, yeah, I mean, basically, if you're going to, what else could you get? You can get bunches of number operators. The whole thing has to be positive definite. If even one of the number operators came with a minus sign, it wouldn't be possible for the whole thing to be positive definite because you'd be able to find a state in which it was negative.
Yes.
So it's more or less going, the structure was built so that it was going to work.
What is the spatial thing? You had a global symmetry, you broke down to its one part, this charge 2 part, which is Q1 square, and then you got different charge objects. One is Q1, one is Q1 dagger.
Yes.
Exactly to make singlets.
Yes, it was important that Q1 was quadratic. Q1 was quadratic in oscillators. That played a key role. Other than that, I think mostly it would just have gone through. But that it was quadratic was very important. Okay, now I'm claiming this is 0. Why is that? Well, let's just use the first you can see by construction. But S is this object, this object. Firstly, it's obvious, right? Because, sorry, this is Q1. It's obvious that Q1 with S is 0 because Q1 counts the number of Q1 was where it was this kind of expression with alpha alpha minus of minus m Cm.
Yeah.
Okay.
But doesn't it just follow from Q1 squared being equal to 0 and then any of the middle ones will cancel out because it's
Exactly. if you look at the expression, this will be 0 because you see those things were weighted with m. This minus m and plus m will cancel. But the more elegant way of saying it is the way you said it. So let's just write it out. This is Q1 times Q1 R plus R Q1 minus Q1 R plus R Q1 Q1. Now Q1 squared is 0. So this term and this term are just 0. So we get R
Q1 R Q1 minus Q1 R Q1.
Q1 R Q1 minus Q1 R Q1, which is 0. Exactly. Q1 a commutator of Q1 with this object here by construction is 0, as he pointed out. Okay? Which you can very easily explicitly check from the explicit expression, if you'd like. What?
Yeah, for that does not depend on the definition of R. For any arbitrary operator R.
Yes, but it depended on the fact that it was anti-commutator of Q1 with something.
Yeah.
Correct. But it's true. It's more general. But it's true here as well. What does that mean?
Is this true? Is this the fact that Q square commutator with R? Does it make sense? No, anti-commutator with R. See, I am not understanding this. What is it? What does it mean? How do you see that this is zero? You do some algebra, right?
You do algebra. You see, this class we're mathematicians. We don't understand anything. We do. I mean, you know, yeah.
Is it obvious that by construction it could be zero because of this?
Okay, you want an analogy?
Yes, S was this Q1 anti-commutator R. All you use that Q1 squared is 0. As long as Q1 squared is 0, this algebra will go through.
Right. You want to know why it worked. You know, it's like this. You're trying to generate, this thing generates the motion of Q1 on the operator R.
Yes.
And this thing squares it.
Squares it. Okay, because it's bosonic, it squares it.
It squares it and therefore it's 0.
Yeah, that. The Q1 squared commutator R, but it's not wrong. But this seems to be a concrete.
Well, this is a physicist's way of understanding.
Yeah.
Okay, fine. Now, because Q commutes with S, this means that the problem of cohomology is well posed in every step. S is a diagonal operator, is an operator that can be diagonalized, as is obvious. Okay? And so the problem of cohomology splits up into an infinite
eigenvalue of S.
Exactly, an infinite number of separate cohomology problems. Cohomology problems in all the various eigenvalues of S. Just like a cohomology problem split up into a cohomology problem in physical subspace. All good? Great. Now I'm going to argue that the cohomology of Q1 is trivial except in the 0 eigenvalue space of S. Okay? And in order to see that, I just use the following. I use that Q1 R is equal to S. So suppose I take this equation, which was a definition, and I act on it on a state which is in the S eigenvalue sector in S. So I'll get S times psi. Now let me look at those states that are annihilated by Q1, those states that are closed and that belong to the S eigensector. Right. We know that the term with Q1 to the right on R annihilates psi, and therefore Q1 on R times psi has to be equal to S times psi.
Psi had charge under S.
Yes, little s under the operator capital S, psi had charge little s. And therefore psi, by dividing through, is this quantity. And therefore psi is Q1 on something else.
Unless S is 0.
Unless S is equal to 0. And therefore psi is Q exact. Q1 exact.
Is this sort of the only way? This is an F and only F, right?
Well, we've shown that if psi is annihilated by Q1, so if psi is closed, then it is also Q exact. There's nothing left to show. Okay? If S is not equal to 0.
And it's in an eigensector.
If we're doing it eigensector by eigensector, and we're assuming S is not equal to 0.
So everything's trivial.
Everything's trivial unless S is 0.
So let me just forget that the expressions of Q and R. There is no expression, but we know the fact that Q1 square is 0.
Right.
From that I compute this S, which is Q1 commutator, anti-commutator R.
Right.
Because of that argument, it will always be that Q1 commutator S is 0, the argument you
Right.
That does not care about it.
Right.
Now, S is an operator like this.
Right.
Therefore, this algebra will also go through.
Right.
So now it's useful to look at eigenvalue by eigenvalue in S sector
Right.
for the cohomology problem.
Right.
Now use special case of X. Yes, how you construct such a beautiful S by doing this, because this is a number.
Yeah. If you're more familiar with geometry, if Q was the D operator,
Yes.
R would be the Hodge dual D operator, and S would be the harmonic, will be del square.
The dy will start B, or start B.
Yeah.
Something.
Forget the homology and the cohomology thing.
I'm just, if you go through the arguments that I used in that, I'm just repeating them.
It's like these times the self-adjoint dagger.
Yeah. Yeah, exactly, the dagger. Okay, del squared is by definition D, and D dagger anti-commutator. So S is like del square. And what we're going to show is that there's one-to-one correspondence between cohomology and harmonic forms. Harmonic forms are those that have 0 eigenvalue under del square, in this case it's S. Okay? So these are all very, for mathematicians, very standard arguments. Just repeating them in a context of use. Okay? Let's keep going. I'm sorry it's taking so long. Okay, so now we've shown that the cohomology, whatever part of it exists in the 0 eigenspace of S. And we want to check whether, how much of the 0 eigenspace. Now, go on.
If you do not have any 0 eigenvalue, then the operator is invertible. So your cohomology will be like totally trivial. So it's that kind of statement. The cohomology is related to the 0 eigenvalue sector.
Yes. 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 Yes.
This is only the Q1, not in general.
Not this is so far for Q1. Then we will, after we understand Q1, we will show that Q1 is the same cohomology as Q. I mean that is a one-to-one isomorph. Okay, so we first do the easy problem, then we do the harder problem. Okay, fine. Let's keep going. Okay, now now I want to show that the object. I want to show that all of the 0 eigenspace of S is in the cohomology of Q. Okay? So, what do we have? If we've got something in the 0 eigenspace of S, we have Q R plus R Q on psi is equal to 0. S. Now, yeah, now how do I make this argument? Just a moment. Of course, in this particular case, we can just look at the zero eigen, but that's not the satisfactory way. Just let's see. Sorry, this is not what's useful. Let's do this. We have Q1S is equal to SQ1 because Q1 commutator S is equal to 0. Okay. Now let's take Q1S on psi is equal to SQ on psi.
The left hand side is 0.
Okay. Now, because we're in this 0 eigenspace, the left hand side is 0. So we have S on Q psi is equal to 0.
Q psi also belongs to the same space.
But now notice one thing. Notice that Q carries ghost number charge 1.
Q carries ghost number charge 1, okay. C
Okay.
charges carries 1.
And if you've got something in the 0 eigenspace of this operator, all of them are 0, so that carries ghost number charge 0. So if psi had charge 0, because it was 0 eigenspace, because it was annihilated by S, Q psi has charge 1. Okay?
That has to be 0.
Therefore, this is a state in the, not in the kernel of S.
Q acting on psi is 0.
Yes.
Because otherwise it is a contradiction.
Yes, I'm trying to make that argument. Saying Q acting on psi cannot belong to the kernel of S. The kernel of S, we've checked, is only states with ghost number 0. But Q acting on psi is ghost number 1.
You told me, but that's telling me that Q just moved psi from the S equals 0 to the S equals 1.
1 state, yes.
But doesn't this
Oh, not necessarily 1. S something.
doesn't this tell me that Q can't mix the S eigenstates?
Q
Can't mix the S eigenstates.
yeah, exactly. That's another way of saying it. That's why Q psi has to be 0.
Oh, okay, right. So, right.
Yeah. That would be another way of saying it.
What did you just
Yeah.
I took the contradiction as a statement and I was wondering
Yes.
if I was wrong.
Okay. So the way I was saying it, which is exactly equivalent to the way you were saying it, is that this thing has to be not in the kernel of S. Now, since S outside its kernel is invertible, the only way S on a state can be 0, if the state lies outside its kernel, if the state if the state itself is 0. Okay? And therefore it must be that Q psi is equal to 0.
We have already proved if psi is in 0 eigenvalue sector, then it's not exact. This.
Yeah, but this statement by itself tells you,
That it's closed.
it tells you that it's,
You know that S acting on it is 0, and you know from its charge that it can't be in the right eigenspace.
Yeah.
It can't be in the S equals 0 eigenspace.
This proves that psi is Q closed.
Q closed. Now, suppose it was Q exact, it has to be Q on some other state at S equals 0. But Q acting on any state on S equals 0 is 0. So it's impossible for it to be exact.
That was.
That's probably what you were saying, yeah.
Okay, so that proves.
Could you repeat the last sentence?
You see, we've shown that Q on psi is 0.
Yes.
Now, suppose it was exact. Since the problem splits eigensector by eigensector, if it was Q exact, the only thing that could have happened is that psi was Q on some other state with S equals 0.
Yes.
But we've checked that Q acting on any state with S equals 0 is 0. So psi cannot be Q acting on a state with S equals 0. It's a general property of cohomology that in a space, if Q kills all states, then it's a cohomology, then all states belong to the cohomology, because then there's nothing for it, there's no exactness left. There are no exact states. This is very specific to the problem. That I agree. That I agree. There was some additional element in here. And we're going to use this ghost number often. Okay, so there was some other conserved charge that we're going to use. Because we're going to use two conserved charges. Light cone, this NLC, I mean not conserved, two charges, NLC and ghost number. Okay, so good. So we have now shown that not only is the cohomology empty outside S equals 0 subsector, we've also shown that the cohomology
Is complete.
is the S equals 0 sector. So we proved that the cohomology is harmonic forms. Okay? See, the charge that we used is simply something under which Q has charge 1 and its dagger has charge -1.
Okay.
It's not a very sophisticated charge.
You could have said. Okay.
Whether a form is even or odd, that kind of thing. That kind of, just raising a something like that. Not exactly even or odd, because that's a Z2 value term, but okay. Yeah.
And strengthen the argument that he was making. But even going back to this thing, this tells us simultaneously that Q can't mix the S values.
Yeah.
Just because I know the charge of Q, I know it must mix the S values.
Yes.
Okay.
Yes, that's what you said at the beginning, and it's I think completely right. Okay, great. So we have computed the cohomology of Q1, and now because we are exhausted, we may not realize the significance of what we've done. But notice that this cohomology from this expression is precisely the light cone gauge Hilbert space. Because, I mean, suppose K was in the 0, 1 direction.
No B, no C.
No B,
plus,
no C, no plus, no minus. That's exactly what we got in light cone gauge.
Yes.
So Q1 has a very beautiful cohomology. It's the Hilbert space of the physical problem in light cone gauge. So if only Q1 was the real BRST cohomology, we'd be very happy. But the real BRST cohomology is some complicated beast. It's not quadratic and so on. So now how do we proceed? So now the next step, okay, I'm sorry for this, okay, for those of you who don't like these mathematical arguments, I'm sorry for this, but you know, what do? Either I tell you it's true or I have to give you the arguments. These are the arguments. Again, let us, it's not very physical, no?
No, they seem very physical.
They seem very physical, okay. Okay. Yeah. So now the next thing is to upgrade our arguments from Q to
Q1
Q1 to
to Q.
Q. Now what was S? Our S was equal to, remember, it was Q1 times R. So what we're going to do is to define S tilde, which is S plus U, as equal to Q times R.
Okay, so U is the commutator with 0 and -1.
Exactly. U is the commutator with 0 and -1. And because U is the commutator with 0 and -1, whereas S has charge 0 under NLC, this has charge either -1 or -2 under NLC.
Okay.
Right, because Q1, R had charge -1 under NLC. Q1 had charge 1, so that's why it made it 0. But if we did either 0 or -1, we'd get charge either -1 or -2. Okay.
And R still defines the dagger of Q1.
Yes, R is not touched. Okay. Now, I want to make the following construction. Let psi.
But now the cohomology of Q is same as 0 eigenvalues of S tilde.
Now the cohomology of Q is the same as 0. Oops, sorry, eigenvalues of S tilde. Exactly. It's the same argument. Exactly. Now I want to make the exactly. So as Indranil said, the same argument will tell us that the cohomology of Q is the 0 eigenvalue of S tilde. All the same things, including the ghost number. Okay. But now I want to find a map between the cohomology of S tilde, I mean the 0 eigenvalues of S tilde and the 0 eigenvalues of S. Okay? So consider the following construction. Psi is equal to 1 minus plus 1 minus plus, right? Yeah. 1 minus S inverse U, S inverse U. Inverse U plus S inverse U, S inverse U minus S inverse U, S inverse U, S inverse U, and so on.
1 over 1 plus S inverse U.
It's 1 over 1 plus S inverse U, but I've done it in a way that I'm keeping track of the operator ordering carefully. Yeah, 1 over 1 plus S inverse U. 1 over 1 plus S inverse U. Okay? Why have I looked at this construction? Okay, first let's first address the intuition that you had. So this psi is equal to 1 over 1 plus S inverse U on psi naught.
So S tilde acting on, S acting on psi is S tilde acting on psi is acting on
Exactly, exactly, exactly. So,
S tilde acting on psi is S acting on psi.
yeah, we want S plus U.
So
Let's-
I'm sorry, the psi 0 was the S equals 0 sector of the one that we did previously, right?
Psi 0 is the exactly. Now let's compute what we get by S plus U acting on this object. Okay, actually it's best just to do it because, yeah, S plus U acting on 1 minus S inverse U plus S inverse U, S inverse U, and so on. From here I get the S. Okay, here I get a U, S plus U, but from here I get minus U plus, and so on. So that's equal to S.
S tilde on psi is psi 0.
Exactly.
Multiply this through.
Exactly. However, what's important, so this on psi naught is equal to S on psi naught.
So multiplicating it now, because we have already proved if S on psi 0 is 0, then S tilde on psi is 0.
Yeah.
Now you
So
have to prove this is the only one, so it's something multiplicating.
wait, first I want to make sure that this operation is not a formal operation. Okay? This is potentially a formal operation because S inverse does not always make sense.
But U acting on psi naught changes that.
Exactly. S inverse does not always make sense because S as an operator has a kernel. However, U is an operator that carries NLC charge -1 or -2.
Now this transformation is invertible, you said.
And this psi naught belonged to the kernel of S. So it had NLC charge equals 0. Therefore, U psi naught has NLC charge either -1 or -2. And S is invertible where NLC is -1 or -2.
Non-zero.
So this operation here, which looked like it might have been a formal operation, is actually well defined.
And once it is invertible,
Mhm.
then you have already proved that if psi naught is in 0 eigensector of psi of S, then this state is 0 eigensector of S tilde.
Exactly.
But this is invertible, so this is 1 to 1.
Exactly. Exactly. And so what we have shown firstly,
Sorry, S tilde has a zero eigenspace.
S tilde has a 0 eigenspace. Yes.
So S plus U is not invertible.
What?
So S tilde is not invertible, so S plus U is not invertible. So I would want this to be, this big expression to be S plus U inverse times S. Times S. But I can't have that either, right?
S plus U inverse times S. Yes.
But I can't really, I'm trying to see, like, forgetting the notation, what is this really?
Yeah, you're right. It's S plus U inverse times S.
But S plus U, I have the same problem as S, it's not invertible.
No, but the point is that it will be invertible except in the sectors which, the only place where it's not invertible are the sectors which are killed by S. Let me say it more physically. What we've got is a lower triangular matrix. You see, let's call this NLC charge, let's think of it as how many rows below, how much below the diagonal U.
Yeah.
Okay? So diagonal elements carry NLC 0. One below diagonal carries NLC minus 1 and so on. So what we've got is some operator which was 0, 1, 2, whatever. That was S. S tilde has stuff here, stuff here, and stuff here. So the whole thing is this plus this. Now where is this not invertible? It's not invertible in this sector. But we're acting on with your 1 over S tilde on S times U.
Okay.
And S annihilates that part.
0 anyways or 0 anyways.
Yeah, that's what I've more formally argued from here. Yeah. Okay. So what we have shown is that there is a we have shown here that given any state in the cohomology of Q1, we have produced a state in the cohomology of Q. Because the Q cohomology is in one-to-one correspondence with 0 eigenspace of S tilde, using exactly the same arguments that we used to show that Q1 cohomology was in one-to-one eigenspace, one-to-one correspondence with the eigenspace, with the 0 eigenspace of S. Moreover, Indranil said this, but I'll just repeat it, and then it's really ridiculous, but we'll have to continue this next class, but 7:30 and yeah, okay. This took much longer than expected. Okay, I had hoped we'd move on to the last formal thing I wanted to do before starting to do physics or going on to the superstring, depending on what you guys want, is to explain to you how moduli spaces of Riemann spaces, explain to you about Beltrami differentials. Then we've got all the techniques in place to understand the string scattering amplitude really well. I thought I could do that today as well. But anyway, let's quickly finish one or two things here. Indranil's already said this, but I'll just say it again. We've already shown that there is that given any state in the cohomology of Q1, we've got a state in the cohomology of Q. But can we show that there is no more possible? Could there be a state in the cohomology of Q?
That's not in the cohomology of
Yeah, could it be that the cohomology of Q is bigger? Okay? And that is basically impossible by this kind of argument. Given a lower triangular matrix, it's impossible to get a larger cohomology than the cohomology of this. Okay? We can make that argument more formally. Or you just I suppose we could just do the inverse map in some way. I mean, basically what we've shown is that the cohomologies, that the 0 eigenspaces of S and S tilde coincide. We've basically shown that.
Because you basically break up some generic state vector into the 0 section and the non-zero section. And then on the interesting section, you sort of have an invertible operator, and the other thing you already know that they match.
Yeah.
Basically, it's invertible.
Exactly.
That's the important.
That's the important thing. Okay, and so what we've demonstrated now is that the cohomology of Q and Q tilde, Q1 and Q tilde are isomorphic, but the cohomology of Q1 was the light cone gauge Hilbert space. So the cohomology of Q is the light cone gauge Hilbert space. The last thing I want to show is that on this physical Hilbert, on this Q cohomology,
L0 is 0. Is it?
no.
Then that's some point.
That we've seen, L0, because we had B's, commutator with B. But last thing I want to show is that the norms, the inner product is positive definite on this space. Now we know that the inner product on light cone gauge is positive definite. Right, because if you've got no B oscillators, no C oscillators, no pluses, no minuses, clearly everything's positive. Okay? However, our state is not a state made out of these oscillators, just in one-to-one correspondence with these. Okay? So, I want to know suppose I've got psi 0, 1. And then I have this business, 1 plus S inverse U plus blah, 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 blah. And then the dagger of that, and psi 0, 2. Okay? Oh, let's say psi 0, 1. I want to check what this inner product is. Okay? Now, this is actually very easy. And the reason is that, what we're going to do, we've got bunches of oscillators here. What we're going to do is to take the annihilation operators through to the right and annihilate things. Okay. Only those things with no annihilation. If your annihilation operators will go to the right and annihilate, creation operators will go to the left and annihilate. Okay? But those things that will be leftover non-zero are those that come out because of commutation relations. But because all U terms here have non-zero NLC charge, and let me say it another way. These objects each had a charge NLC equal to 0. Now, no expression built out of oscillators has a non-zero matrix element unless the net NLC charge adds up to 0.
Yes.
So anything involving the U's.
No, U is U dagger or something. There is a dagger.
There is a dagger.
So U is doing something bad, I agree. But what about the dagger?
Yeah.
Sorry.
Good. No. This is a good point. It's a good point. It's true. Wait, let me think that through. Wait, let's see what he says. No, but sorry. Let me say it this way. Consider this object. Okay, this whole state here is a state Okay, I'll first make the argument and then I'll give you an example. Consider this whole thing. This whole thing can be broken up into a state with NLC charge 0, NLC and NLC charge negative. Okay, now claim the inner product between any two states can only be non-zero if the NLC charge of those two states adds up to 0. Okay? So let's see this. Let's see an example, for instance. Okay. So suppose I've got some vacuum, and I get alpha.
This statement I agree.
This statement you agree? So then it follows.
But the dagger is the K.
No. There's no dagger. I'm saying inner product. Take a state. Take the inner product of that state with another state. I'm saying, think of it just in terms of states.
Okay. Let's think about states. Yes.
Okay. Then the inner product between any two states can only be non-zero if the sum of the NLC charges is 0. You see, because plus and minus don't change under dagger. Okay, let's take an example.
Yeah, let's take an example.
Okay, suppose we had 0 and we had alpha minus 1 minus. And we had another alpha minus 1 minus on 0. Now let's take the dagger of this. What this does is changes alpha minus 1 to alpha plus 1, but it keeps it minus. And so now when you take this through, you'll still get 0. See, the dagger is not flipping the plus minus charge.
That's the thing. That's the thing.
Yeah, it's what you said at the beginning of the class, that the plus minus is some symmetry that has nothing to do with the well sheet.
What is it? That's the reason that. Okay.
Okay? So you see that it's clear that you can only get something non-zero if the charges of the two states, whose inner product you're taking, add up to 0. Okay? But that's impossible except in the 0 sector. Because this state is a state with NLC equals 0 plus state with NLC equals something negative. We'll only get add up to 0 if we take 0 with 0. And therefore the inner product of these states is the same as the inner product of the corresponding states, of the corresponding light cone gauge states.
Because one is the only thing that is clear.
Exactly. And therefore we have shown also that inner products in Q cohomology are those of light cone gauge and therefore positive definite. This is an incredible thing. Notice we have shown this for a particular representative Q cohomology. But it doesn't matter at all which representative we choose, because if we take a particular state Q and add Q times alpha to it, then the inner product of that with any Q closed state is 0. So once we've shown that it's positive definite in some representative, that's enough. Okay? So this statement here is what's called the no-ghost theorem. That is, that the BRST cohomology of string theory has no ghosts. That is, on the world sheet it's positive definite norm, and that in fact that it is the light cone gauge cohomology. Okay. Now the last, I wanted to show various other things, but I'll just leave these as exercises for you. Okay.
No, please, the module is please tomorrow or today, please.
The Beltrami differential business. Okay, I'll do that. No, but just about this no ghost business I wanted to show. There are. Okay. One thing I want you to check. Okay, you try to check this and I'll check it for you in class this one, next time. I want to claim that this state that we have produced takes a very special form. That it is of the form C times a matter primary. That every state that we get by starting with, you see, of course, light cone gauge is very special. It's made up purely of matter states, oscillators. Now we act something on that very special state with something we know. Claim is that we get something of the form C times something that is purely made out of the matter sector.
Action of this operator you are saying will be this.
We'll give you this, acting on a light cone gauge state. This is one thing that I would like to request you to check if you can. Then all this I'll probably quickly go through next class. Next thing I would ask you to check is this. That if
I'm sorry, you mean that these states are dual to an operator that can be expressed this way?
that's right. Next thing I want you to check is now if we take Q, the action of Q on this. Okay? Check that the action of Q on this gives you is equal to 0 implies that ln on V is equal to 0 for all n greater than or equal to 0. Namely that V is primary. Okay, and Ln is equal to
This is matter plus cost, right?
the matter plus cost. If we keep it,
it would have given some number
yeah, would be equal to delta n0
for matter.
for matter.
This is total.
Yeah, Lm, let's say. Okay, so what this will tell you is not only is this representative C times V, it's a dimension 1, V is a dimension 1 matter primary. Next thing I wanted you to check is that if we take V goes to V plus L minus M on chi. Okay, then CV, V goes to, yeah, CV is equal, CV minus CV tilde is equal to Q1 something. Q commutator something. Yeah. Okay. What the upshot of all of this will be is that we found our construction has given us a nice representative of BRST cohomology, acting entirely where the ghost part is trivial. It's just an explicit C. Everything's in matter. The matter state has to be a dimension 1 primary. Moreover, two different matter states, the two different dimension 1 primaries that differ by a descendant, are to be treated as the same primary. Okay? This will give us a way of thinking of the space of BRST cohomology in a way that is not just correspondence. But for counting, we've got the Lycone-Hilbert space. But we will have a way of constructing, just from the matter part, a cohomology, a representative element in every cohomology. Okay? What we want is those dimension 1 matter primaries modulo things that are both primaries and descendants.
How can something be primary and descendant?
It can't if the Hilbert space has positive norm. A state that is both primary and descendant is null, because if you look at chi, which is a primary, that means that Lm on chi is equal to 0. Okay, but chi is equal to L minus M on psi. Now dot it with chi. Lm acting on this gives Lm on this.
And since they're the dagger,
Yeah, which is 0 because Lm and chi is 0. Okay, so something that is both primary and descendant can be if the state is null. I'll give you examples next time.
So our Q exact states were null states, and are we saying now that null states are Q exact states?
Our Q exact states were null states, and
Now we're trying to show that now we're showing that a certain class of null states are
I'm showing that within this particular class, see,
some class of right.
what I've done is take the equivalence classes of BRST cohomology and gone to a smaller equivalence class. I've not gone to one state. I've gone to a smaller subclass. The subclass of operators that can be written as C times V. Now that subclass is still an equivalence class. C times V, V is a matter 1 primary, it's Q closed. But we've not completely fixed the equivalence classes. The ambiguity of equivalence classes there is the set of V's that are both descendants as well as primaries. Shifting by those gives you generates the remaining equivalences after having partially
Do we
fixed.
know that do we know that this exhausted all the remaining equivalents?
I will prove that.
This statement is even if it is true for m greater than equal to to 1,
Mhm.
then you can argue this thing. Let's talk about state.
Yes, yes.
With matter
Yes.
primary.
Yes.
So that for m greater than equal to 1, this equation is true.
Yes.
And
That.
they are descendants, therefore at least L minus 1 is acting on some other state gives them. I am just repeating this argument.
Yes.
When I have a matter primary field,
Mhm.
I have a matter primary field for which L0 acting on this gives some number times that.
Yeah, it doesn't matter what the number is.
But L1, L2 all kills.
All kill it.
So using that information, and if I assume that the same state is a descendant,
Yes.
I can say the same thing. That is
Yeah. This only use.
argument does cares about
It didn't use L0. Yeah. Okay, we better stop now, and we'll continue next week.